Today we're starting our last topic of exam review, which is integration. And if you remember when we started integration, we at first talked about how it just represents area under a curve, or better yet, between a curve and the x-axis. For example, this symbol means area between a curve and the x-axis. This is asking us to find the area from an x value of -2 to an x value of 5. Between this curve, which we'll call f, and the x-axis. Thankfully, this curve is made up of straight lines, so we can actually find that exact area under the curve. We start at -2 and go to 5. The easiest first section is from -2 to 2, and creating this triangular area. This has a base of 1, 2, 3, 4, from -2 to 2. And a height of 3. So 1/2 base times height tells me this has an area of 6. Our next area that's easiest to find between a curve and the x-axis is this triangle right here. It has a base of 1 and a height of 3, giving us an area of 1.5. And then the last piece is a base of 2 and a height of 3, again giving us an area of 6. It's important to remember, however, that if we're moving from left to right, then area above the x-axis is what we call positive area, area below the x-axis is negative area. So we have a positive 6 minus 1.5 minus 6, meaning that that integral, the area between the curve and the x-axis, is actually equal to -1.5. When we first started working with area like this, all we had were semicircles and straight lines, triangles, rectangles, trapezoids, to be able to find that exact area. But we talked about how we don't always have straight lines and semicircles. And when that happens, we use a rectangular approximation known as a Riemann sum. So if we're trying to find the area under a curve that's not a straight line or a semicircle, we can use little rectangles, anchoring them on the left-hand side or on the right-hand side to approximate the area under that curve. We also talked about how the skinnier those rectangles are, the more accurate it is. But putting rectangles underneath a curve, you can never get that exact answer, no matter how skinny they are. And so what we did was we let our rectangles get infinitely skinny. We looked at the limit as delta x goes to 0 of that sum. And that turned it into the most exciting day of the semester, where we learned the fundamental theorem of calculus. The fundamental theorem of calculus, through that pretty complicated proof of the mean value theorem, tells us that if we want to find the exact area under a curve, let's say this curve is f prime, we can anti-differentiate our integrand and plug in our bounds. That is super powerful in giving us that exact area under the curve. All that we have to do is anti-differentiate, plug in b, and plug in a. It is also really, really important that you realize that this tells me the net change in my function f. If I integrate the rate of change of f prime, the rate of change of f, I get f of b minus f of a. That tells me my function value at b. I subtract off where it was at a, and I get the net change of my function from a to b. That's a point that we will come back to later.